Dear students, today we will be taking up this reaction, Stille reaction. This is a efficient and good method for CC bond construction. Why? Because it has got mild operating conditions, high functional group compatibility, very useful for the synthesis of natural product. One such example I've given here, this marine alkaloid. It's in A, which is having anti-tumor activity. At the same time, it is used for the synthesis of anti-cancer drugs, antibiotics, organic dyes, and also finds applications in photovoltaics. The reaction has been depicted, a general reaction, Rx R-M in the presence of a catalyst, palladium catalyzed, as I mentioned earlier, like the Heck and the Sonogashira reaction, which we've done, gives rise to this coupled product RR- with the elimination of MX. RR- are generally sp2 hybridized. At times, of course, in Rx we can take, there are evidences that they have conducted certain reactions using an alkyl group. X is iodide, bromide or triflate, good leaving groups. Catalyst is palladium and organotin, so M is tin. The metal is used here is tin. The reaction cycle or the catalytic cycle, as we can say, is similar to the ones which we have done earlier. All of them follow the same sort of steps. So similar steps are followed. This is the catalytic cycle. As we can see, in the catalytic cycle, how does it start? It is similar, all the steps, the three steps are similar. First of all, oxidative addition, then transmetallation, trans isomerization, leading finally to reductive elimination. By now you must have got very much familiar, in fact must be knowing very well as to how the catalytic cycle in these palladium catalyzed carbon-carbon coupling reaction takes place. So this is oxidative addition. Oxidative addition implying that where palladium 0 is changed to palladium 2. So palladium 2, here we can see what will be happening. Addition, oxidative. As a consequence, oxidation state is increasing of the central metal palladium. At the same time, electron count is increasing. At the same time, the coordination number is increasing. So oxidative addition, after that is followed by transmetallation. Transmetallation, that means that the organotin R3SN R1 is the group which is being transferred across to the metal palladium. Hence the name transmetallation. So with and R3 is generally BU3 many a times. So R1 will be transferred, as can be seen over here, and we get this RR- attached to this palladium. Why? Because R- has been attached, X leaves with tin, and in place of that we get R1. From here X has left with tin and we get this. After that, trans isomerization occurs, and trans isomerization is a necessary step in this, because what will happen after this? These two will be coupled. So from trans, because trans is the stable, thermodynamically stable state. So after oxidative addition, here what we are getting is the trans. The oxidative addition takes place in a trans manner because that is thermodynamically stable. But then before reductive elimination, this step is occurs prior, because R and R1 are coupled. So we get R, R' or R1, and reductive elimination, just the opposite of oxidative reduction, that PD2 is again changed to PD0 and the cycle continues. It combines again with Rx by oxidative addition to give us this product. So this is the catalytic cycle of which we have seen earlier in the case of Heck and Sonogashira reactions. The same catalytic cycle occurs here, except that of course in this case we are taking organotin. The stereochemistry is retained. Whereas the regiochemistry is difficult to control in palladium catalyzed reaction, so it is controlled by means of optimization. So the Stille reaction, as we can see, is a very efficient and important method for construction of the carbon-carbon bond. Now let us see to these steps. The oxidative addition step, the first step. Oxidative addition is taking place with Rx, and PD0 is being changed to this PD2 state. A trans product is formed because we know trans is more stable. So a trans product is formed. And then by transmetallation, when this occurs, there is trans isomerization. So before reductive elimination. So now transmetallation occurs, and transmetallation means that this group R1 is transferred from this metal across to this metal. Hence the name transmetallation through a 4-membered cyclic state. So R3SNX, this leaves, and in place of that, R1 has now been transferred to palladium. So the transmetallation step leading to this palladium complex. This, prior to reductive elimination, because this is a trans product, so it undergoes trans isomerization so that R and R, they are able to couple, and PD2 is again changed to PD0. Reductive elimination is just the opposite of the oxidative addition. So R and R dash, they are coupled to form the product, and PD0 is formed, that is reductive elimination occurs, the opposite of oxidative addition. Let's see one or two examples. This is one example. Here the triphthalate that will leave with BU3SNOTF, and this will be coupled over here to the double bond, as can be seen in the product. Another interesting reaction is carbonylation reaction, where this sp2 hybridized, this Ri, reacts with this organotin. This time we are using pH CH, that is associated with tin. So in the first step, which is common for all the reaction, is the oxidative addition with palladium occurs of this halide, sp2 hybridized halide. The first step is oxidative addition, and in the second step in this, before transmetallation, the CO is added across here. It is added here in place, and this is inserted here, CO. So this is a very versatile technique. And in the last step, after this, when transmetallation occurs and reductive elimination, that is PD2 is converted to PD0, and at the same time transmetallation, that is this group is transferred across here. This is the product. This is formed together with the insertion of CO under pressure. So this was another interesting example of Stille reaction with carbonylation. And as we can see in these reactions, the versatility, that is a number of different types of products can be formed depending upon the substrate and the organotin we have selected. So organotin can be made compatible with a number of other functional groups. Compatibility it has, because let us see this interesting example here, where you will recollect one earlier reaction that we have done, that is the aldol condensation. Looking at this, you won't expect this to be a coupling reaction, but as you can see, the fourth reagent here which is added is an organotin reagent. So what will be happening? Can anyone think as to how this reaction must be proceeding? See, LDA, if you recollect a little about aldol, then you will remember that there is something which is called as directed aldol condensation and its regioselectivity. And how is the regioselectivity done? By using a base which is hindered. So this is lithium diisopropylamine. So what will happen, because this carbonyl is having a functionality here, the carbon hydrogen here, the alpha position, we know it is acidic. In the presence of a base, a carbene ion will be formed. Carbene ion can be formed from here or here, either of these two places. But since this is a hindered base, it cannot attack here. So rather than the thermodynamic, we will get the kinetically controlled product. So it will attack at this position, which is less crowded, LDA. As a result of this, the less substituted alkene will be formed at this position, as we know. So this type of a kinetic enolate is formed. This kinetic enolate, and what is the function of PHNTF2? Let me tell you, this is known as Comyn's reagent. It is just there to introduce triflate, the group triflate. The group triflate is introduced here. If any of you are interested, you can look up the structure. I've drawn the structure of Comyn reagent. This PHNTF2, which is known as bis trifluoromethane sulfonyl aniline. This is the structure of this reagent, PHNTF2. See, this is C6H5NH2 had it been aniline, which is substituted, hence the name bis, by trifluoro. This is trifluoromethane C sulfonyl. Two such groups. So this is PHNTF2, Comyn's reagent. And what will this do? Just transfer this group across on the ring, because this is a good leaving group, to form triflate, which is trifluoromethane sulfonate. This group will be transferred. This, which is present here, this will be transferred to RO. That is, this over here, which is formed, are kinetic enolate. So this is the function of this Comyn's reagent, to form a triflate. So with the result, what will happen, that once we get this kinetic enolate, let's come back to this, on hydrolysis, after hydrolysis, we get this kinetic enolate. This will then react with our organotin, a compound organotin, and this organotin here, this will form this type of a product. So this is the product that is formed. Let us see in the second case. In the second case, where we have taken a weak base. Again, recollect our aldol condensation. This means this time we get the regioselective product, that is here we get the thermodynamically stable. So regioselectivity, rather than the other enolate, we are getting the thermodynamic enolate that is formed. And the reagents are similar as were shown earlier. So in this case, this double bond will be formed not on this side, that is not the kinetic, but the thermodynamically stable, because this is the hindered side. Now this is a small base, so this is a more substituted carbon over here, so the double bond will be formed over here. Hence the thermodynamic stability, this thermodynamic enolate will be formed, which will be converted by this Comyn's reagent into this triflate, which will react again with this organotin compound. This is the organotin, and this group will be transferred. So this time, that is the only difference. This will be the product that will be formed. So remember, if we have taken LDA in that case and later on gone for still coupling, then we will get a different product. On the other hand, if we have taken a weak base, in that case, this will be the product that will be formed. So in this case, the earlier case that we did with LDA and Comyn's reagent and this organotin compound, this was the product because the bond was on the less substituted side. So coupling took place here, or the double bond. Here, the double bond which was introduced in the other case with LDA, without LDA, when OH was the weak base was used, then we got a thermodynamically stable enolate, which led to this type of a product. So this is all for today. The still reaction, we did a very important reaction by way of carbon-carbon bond construction.